Welcome, everybody. This is our pleasure to introduce Patrick Bryant is going to tell us about Umol, the Universal Molecular Framework. This is our bi-weekly molecular modeling group reading group meeting. I hope you can come back and join us if you are watching this on YouTube, or if you're live, come back in 2 weeks. We're typically molecular modelers, but we're interested in the details and logistics of how to actually use these methods. And we're really pleased to have Patrick come and tell us about it today. Patrick did his postdoc with Frank Noe in Berlin and is going to start his group now in Stockholm. So look for his position there, and it sounds like he might be recruiting sooner than later. So thank you, Patrick, and take it away.
Thank you. Thanks for having me here. I'm going to present Umol, which is supposed to be a universal molecular framework, but it's not universal yet. So now it predicts protein-ligand complexes. And I plan to extend this to protein anything, really, any type of atom. But why not do anything, then, you can wonder. And this is because we have coevolution. And proteins have evolved. And this is kind of what all of this is based on, right? This is the foundation of protein structure prediction. That amino acids that mutate together are more likely to be in contact in a 3D protein structure. So what we do is that we look through evolution. We take a protein sequence and we search a protein sequence database, and then we find similar sequences. And from this, then we can look at what positions mutate together. And these positions are also likely to be close together in the 3D protein structure. And this kind of constrains this whole problem, right? So if we can find the graph of what amino acids are in contact, we can predict the structure. And this is how you do NMR and so on. So this has a lot of precedence. But there is no coevolution for ligands. So previously, protein structures were required as input to kind of dock ligands together. But the problem here is flexibility. So, I mean, there are so many ways that the protein and the ligand can kind of move relative to each other. So this is like a huge search problem. Even if you have a very good scoring function, it would take so much time to kind of search the possible space to reach a conclusion. And this same problem existed for protein-protein docking before we had AlphaFold and AlphaFold multimer. But if you can get kind of coevolution between proteins, you can get much higher accuracy, as I've shown previously. And molecular dynamics can perhaps help with this flexibility. But the problem is, of course, the scaling, the search. It's a little too slow if you want to do this large scale. You can never screen many ligands with this approach, even though you could perhaps do this in a very targeted way. And this is the same problem starting from unbound apostructures from proteins. So there are so many possibilities. And also sometimes larger arrangements are required, and this none of the methods that exist today can really handle that well. So the solution that we and now others also propose to this is to instead do some kind of protein-ligand co-folding with deep learning, where you try and fold both the protein and the ligand structure together from sequence information. So the protein, how do we represent that? Well, we have to use the MSA somehow, because all protein constraints are really in there. So what we do is that we take the protein sequence and we run HH-Blitz on unit class 30 only to get our MSA. And the reason for doing this is that it's very fast. And you only need very little disk space. So you can download and install this database and it splits in around 15-20 minutes. And then you can basically run the whole software. As compared to using more databases that are bigger, from example, metagenomic reads, it takes basically a day to download it, and you also need at least 1 terabyte of disk space. So this is something we try to do so more people can use it. And the ligand then, well, we start from a SMILE string, and then we input this into RDKit. This is a Python package that is used for everything regarding ligands. And then we do one-hot encoding of the bonds, the atom types, and the ideal bond lengths. So the ideal bond lengths we get from just sampling one conformation with the RDKit. This is basically a flat thing, so there's not really much information in there. And there's no real information on constraints either. If you compare this to the coevolution for the protein, it kind of tells us what residues are supposed to be close to each other in a kind of graph. We don't have this here. And especially, there's no information about protein-ligand constraints. So this is really the big problem. How do we kind of solve this? And to do this, we then do some type of AI, and we input the protein sequence, but we also use target positions. So this is kind of loose definition of anything that has C beta 10 angstrom from any ligand heavy atom. And we then input the MSA that we create with H splits. And in the same representation, we also need to process the ligand atoms, kind of keep these shapes consistent. And this also kind of informs the network about the size of the ligand. But as I said, we don't have any information here. So all you have is really gaps. And this is very similar to what AlphaFold do, but we have the ligand here with gaps as well. And then we also have something called the pair representation, which represents the relationship between each amino acid and each ligand atom. And this is also very similar to what AlphaFold do, but we also have ligand atom encodings. And we don't have any information here, right? So we don't know anything really about how the protein or ligand should go together. And yeah, we one-hot encode this information. So mention basically we have a single double bond, what type of atom you have, and the ideal lengths that should be there. Then this information goes into the main network. And this is very similar to what AlphaFold do as well. You have two tracks. You have one track processing the MSA, and this performs row and column-wise attention to kind of capture the coevolution within the representation of the MSA. And this is then multiplied together to kind of extract things that are in the row and the columns, kind of combine. And we also process the pair representation using triangle attention. And this allows really each position to attend to all other positions and information really to be passed between all positions. And then we take the first row here from the MSA representation and the entire pair representation, and we input this in the structure module. And this is also, again, really what AlphaFold is doing. So the network is very similar. And we co-fold this with the invariant point tension, which is basically just an addition of the first reference frame to attention. To kind of create a kind of bias. And we map amino acid atoms according to the backbone frames. But for the ligands, we don't have any constraints. So this is more like a gas, you can say. And this then goes into RDKit, which we use to generate conformers with the predicted constraints, and then we relax the whole thing. And we get then structure of the protein-ligand complex. And here you can see an example, and you have the native structure in gray and the predicted is color here. So why do we then generate the conformers from restraints using RDKit? Well, this is related to the training. There's a kind of battle between the protein, the ligand, and the relationship between these two. Because if you are really only 0.1 angstrom off here in the ligand predictions, the bonds become chemically invalid. And this has been a big issue with some deep learning methods, that you get things that are kind of in the right position, but the chemistry is not accurate. So this is kind of the solution we provide for this. And why don't we just constrain it then? So why don't we just kind of force this mapping? It has to be chemically valid. Well, this is because it hampers training, we noticed. So we need this full flexibility to be able to learn the interactions stepwise. If we constrain the ligand too much early, nothing is really being learned. So this is a takeaway message from this. But why don't we then map the ligand from some type of frame, like we do from with the amino acids, where we use the backbone frames? And maybe this is a good idea. I don't know, but to me it is a little confusing, because there are many ways to define frames within ligands, while in the protein all frames are the same. And I think this can confuse the network. But this is nothing we really looked into deeply. And as I mentioned, by using an RDKit, we can fix these issues here. As you see, this ring here is completely wrong, right? And this is if your reason kind of the competition of getting the side chain super accurate compared to the ligand. And I mean, in reality, even if you do experiments of the structure, you would never have this type of accuracy, right? So instead, we basically generate 100 conformers and align them to this, and then we get something that is chemically valid. So everything we predict here is also chemically valid. And the protein, it also has clashes. And this we fix with the relaxation with the OpenMM. So we don't fine-tune the net to fix clashes, which you could also do. You could add a kind of clash score after you kind of reach maximum performance. But what we see is that there's a cost associated with learning this protein-ligand relationships. So you have to kind of somehow compromise on accuracy of the protein, I think. And during training, we observed that when the pocket RMSD is really high, the ligands are more accurate. So what you have here is median pocket RMSD on the validation set, and then you have the fraction of ligands that are successful, that have an RMSD below 2 angstrom. And you see here that there's a relationship between these two. So it's much easier to kind of overfit to the protein. I think this is my kind of intuition. And the OpenMM, it can kind of fix whatever errors you have very easily. Since this is just, I mean, you don't really see the difference between these two structures that much now, but if there are any clashes, which we observed in 12% of interfaces, these are basically just resolved. So you get 0% clashes. And yeah, here you can see a comparison between relaxed and unrelaxed structures. So there's very little movement going on here. The losses we use is a combined loss function, which is also very similar to what AlphaFold did originally. But there are some important differences. For example, with the frame aligned pointer, which tries to kind of align each frame and then look at how the positions are off if you look from that frame. The problem here is, of course, that we don't use any frames for the ligand, right? So each ligand is only one atom. So the FAPE, it's only seen from the view of the protein. Nothing's really going on from the view of the ligand. And then we also have this aux loss, which is a combination of FAPE, angles, and also deviations from ideal bond lengths. And this is something we added in to constrain this a little bit. So some ligand atoms don't jump away too much. Then we also use distance loss, which is cross entropy on basically pairwise distances mapped to beams. We also have a language model loss. We mask residues like in AlphaFold, and we do cross entropy on that. And we also have PLDT using C alpha for the protein and all atoms for the ligand. So for the ligand, it's really much more fine-grained than it is for the proteins. And this is also cross entropy loss. So why do we use the overformer architecture? This is basically a copy of AlphaFold 2 with modifications. We don't use template track, and we also handle ligand atoms. And the reason for this is that I find this to be very efficient. And it seems to work extremely well for proteins, and it seems to be okay for protein ligands. We also train some things on RNA, but we'll not talk about that today. And I think the focus to kind of make this better should rather be on getting better or maybe more data, and also engineering better loss functions. Because I think FAPE is great. I mean, that's really why all of this works, especially for proteins, but it's very exact. You're not really allowed any uncertainty there. And I think this can be needed to handle small deviations that are present in protein-ligand interactions, as I mentioned. So how do we train this? Well, we don't have that much compute like Google and other people have. So we only use really one node, which is 8 A100 GPUs with 40 gigabytes of RAM. We could perhaps use more, but we have a terrible cluster and we can't queue whatever we like, and there are a lot of other problems as well. So this is really very small. Most people would maybe say that this couldn't be done on this, but they are obviously wrong. And here you see the LDDT during training, and we colored in a protein and ligand. So you can see that the protein is learned here much faster. This is much easier to learn, while the ligand is not. And this is because you have co-evolution, right, to constrain the whole problem. But for the ligand, there's really no information. There's only the atom types. But they are kind of learned together also. So here you see protein LDDT versus ligand LDDT. And then we color this by the step. So this is kind of the last step. And you can see that the protein is learned easier here, but the ligand kind of follows. So there is some kind of relationship that is being learned there together. And then I also mentioned this with the success rate and the pocket error. And this is of all atoms in the pocket then. And you can see that there is some kind of competition here going on. And I think to kind of make this better, you have to find the sweet spot where the protein is, you know, a little more wrong than the ligand, or vice versa. We crop the protein ligand representation to 256 residues to fit this in RAM, and the ligand atoms are always included here because if we chop those off, I think it will be too difficult for the network to kind of understand what's going on. So the protein size is basically 256 minus the ligand size throughout the training. We also use standard things here, learning rate of 0.01, and we also clip the gradients on the batch with the global L2 norm. And here you can see the losses. So this is the overall loss, and here's the structure module. And what we do here at this dashed line is we introduce ligand constraints, and then this makes the network kind of learn this better. That's why you kind of see a jump down here. And why we don't do this early or in the start is because, as I mentioned, you kind of don't learn that much, and it's too constrained. So you need to keep things very flexible for this to work. It's kind of what I found, at least. And you can also see there these big spikes throughout all of the training. And this is from the histogram loss. And I'm not really sure exactly what's going on there, but I think the network kind of tries to, you know, make things a little bit better, and then it messes things up. And this is something I've observed training on only proteins as well. And I think Mohammed Al-Karishi, when they trained this OpenFold, also talked about this. So we validate every 10,000 steps on clusters with below 20% sequence identity. And here you can see the training step versus the fraction of ligands that have below 2 angstrom or message. So this is the success rate that we use all the time, right? And this is from classical definitions. Since we only do this every 10,000 steps, it's kind of low res, but you can see that at 40,000, it's the best. And this is what we use then to for all tasks, validation, and then testing also this post-bounders test step. But beware here, because it's very easy to overfit, especially to the protein. So that's what I think is happening here, and this is not that many steps. Normally, if you train something like this, I think you would train to at least double, to at least 80,000, and probably then fine-tune it even longer. And yeah, I think this overfitting really comes from that it's so much easier to learn the protein than it is to learn the ligand. Yes. So if you train this until the loss stops improving, I think you can get the pocket pretty much perfect. And perhaps this is useful to predict the pocket very well and then use some other tool for ligand docking, I don't know. But the ligand gets much worse than if you stop early. And this also is kind of related to that the performance is lower for all other deep learning methods that we analyze, including our own, when you evaluate on dissimilar sequences with low homology. Yeah. And you can see this here when we compare it to Rosetta Fold all atom, which has kind of similar performance to us on this whole test set, but they don't use pockets, which we do, and they use templates and we don't. But if you look at the success rate on proteins that have less than 30% similarity to what has been trained on, I mean, this is much lower. We're also not that good. We're about a third in accuracy here. And yeah, I think this is really related to how to kind of balance this thing and not learn coevolution too much. So this is really what I think the evaluation should report, and not really overall, because otherwise we're simply measuring the level of overfitting. I mean, I think if you, since most of these sequences are also more similar to what's in PDB today in the training set, I mean, if you simply overfit those perfectly, you would get the really high score of maybe 70%, but it doesn't really say anything. So that's why I also urge others to release their methods so we can really verify what they're saying. And here are some results then. So we compare with, what is it, 8 other methods here. And you have the success rate, which is the fraction of ligands that have an RMSD below 2 Ångström with the native structures. And we are a little better than resveratrol on this, but the classical methods, Vina and Gold, and Vina is still the best, especially if you look here below 30% sequence identity. This is consistent. The problem is, of course, that you need the hollow structure as input. And I would also advocate for a more flexible scoring scheme, since the 2 Ångström RMSD threshold, it only makes sense if you have the crystal, and this is related to alignment problems. So now we align the C alphas in the interface, and then we take the RMSD of the ligand from those alignments. But it may be that, you know, you just have some side chains that move a little this way or that way, and then you're out of this 2 Ångström limit, while the interaction between the protein and ligand may be correct. So I think you should rather measure the relationship between the protein and ligand if you are to predict the structure of both. And you can see here, we plot RMSD threshold versus success rate at that threshold. And at just above 2 Ångström, we are outperforming these classical methods as well. And at 3 Ångström, we're actually 10% better. So this is why also I talk about this. Another nice thing is using the predicted LDDT, like in AlphaFold and AlphaFold Multimer. It can be used to select accurate ligands and also accurate pockets. So we bind the LDDT here in steps of 10 above 50, and here you have the RMSD. And you can see here that if you're above 80, I mean, the median is below 2, and if you're below 50, I mean, it's around 5. So you have basically nothing successful here. So this can be useful in selecting accurate dockings. And the same is true for the pocket, but this is, of course, much easier to predict. So it's kind of high consistent there. We also have some examples. You see the native structures in gray, and then we colored in the predictions. So you see here some loops are off, or maybe in a different configuration. I don't know. But the ligand and kind of overall structures highly accurate. And I would say these loops are also pretty correct. Even when you have something inside here, it manages to put the protein structure around. And the structure may also be a little wrong in other parts. Like you see here, these alpha helices are not correct, but the interface here is still managed correctly. We also looked at targets that are difficult. So we took basically the 5 hardest targets where the RMSD is the highest on average across all of these 9 methods that we evaluated. And we tried to kind of figure out what was wrong, but I'm not sure that we found anything. So what we can see is that when you have kind of large, complicated things, you can get things in the wrong orientation. So here is supposed to be a heme group that is kind of flipped, and the same here. So we didn't understand, the network didn't understand that it was supposed to go the other way. But in the other 3 cases, we actually do pretty well, where the other methods don't manage at all. So this would be considered accurate, right, according to this 2 Ångström threshold. And these are very close, so they're pretty good, but not quite there. And then we try to look into what explains this difference, since it's not that clear, but we don't really find anything. And the strongest kind of indication is how well we can generate a conformer, or how different the conformer is from the initial raw prediction. But this still, I don't think, really tells anything. So I think this really shows us how little we understand about protein-ligand interactions, and how complicated things are when you don't have coevolution to constrain them, because you can literally have anything interacting. One thing that I think may explain this, though, is affinity. And this was something that a lot of people asked in the beginning when we released this, and we were actually working on this at the same time. So here you see KD from a held out test set, and you have the ligand PLDT here. And the reason why we have these bins, we only have one in the range of 10, is because we don't have anything below here. We didn't have any more data, so there's not that much affinity data on things we haven't seen. But you see the log scale here, so we can actually distinguish high affinity from low affinity really well, just looking at the ligand PLDT. And this was something we didn't train for, right? So I think this is quite interesting. And if we zoom in here and look at really high affinity, everything below 10 nanomolar, we have a very strong correlation with the ligand PLDT. And this is interesting to me, because I know that this data is super noisy. It can basically vary with a factor of 100 sometimes. So this is quite surprising, and I think then maybe you can use this also to select your ligands, both for accurate docking poses and affinity. And perhaps this explains some of the wrong predictions, like I mentioned. Maybe these are just low affinity. So I think we're missing some information there. And to conclude this, why should you use Umol? Well, you have chemical validity, since we use RDKit. So we ran Postbuster's recent preprint on the chemical validity of ligands, and 98% of this test set is valid according to them. And you can also get affinity, which is surprising. And we only use sequence information, so there's no templates or anything. So everything is really flexible. It's only constrained by the coevolution. The cons is that you need a pocket, and this is something we plan to remove in the future. And the performance is still only 45% and 35% below 30% sequence identity. And how to get to 90%, I don't really know. I think we will need either more data. Maybe this will happen with future developments in the structure determination. I don't know. But right now, I can't really see how we can double the performance using kind of the same data. We also relax the structures, but this, I think, we can really fine-tune away quite easily. And on the other hand, this is pretty fast, so it's not a real limitation, I think. It's also very lightweight, and it runs in Colab. So as I mentioned in the beginning, we only install or we download Uniclass 30 and HSplits. So this only takes 15-20 minutes, and then you can run this. And the Colab is available for everyone, right? But it's then more constrained on the size. Thank you very much for listening, and also thanks a lot to Andrea, Atharva, and Frank, who worked with me on this project.
Awesome, thank you. All right, any questions?
Hey, Patrick, can I have a question?
Yes.
Okay. Yeah, thank you for the great talks. And I guess maybe current limitations is like we don't have super good ligand database like that represents the flexibilities of whole ligands, right? Is that?
What was that?
Oh, sorry. Maybe current limitation of like ligand prediction is you said there's no good database for like so many poles of ligand or something like.
What do you mean? I mean, you have the PDB then, or PDBbind.
Oh, but the ligand is very flexible and maybe there's no database that shows so many poses for ligand.
Yeah, I mean, that's true. There's only one pose
I
in all
see.
these crystals. I mean, yeah.
And do you think it is possible to use like partially MD data to learn the ligand flexibilities or something? Maybe that might take so much time for learning, but once it
Sure,
learning
but
is done.
you can never really outperform MD then, right? So you would learn like a faster way to do MD, and then you have to assume that is correct. And I mean, you don't really have any experiments for that. So I think you may be heading into a trap doing that.
I see. Okay, thank you so much.
More questions? Yeah, Joanna, go for it.
Yes, that was a really interesting talk. I hope you can hear me better than the colleague. I actually have maybe one question for now, because I hope we can continue later on, because I haven't really understood what are the limitations of Umol tool when it comes to the proteins which are enriched in unstructured regions. So in example, you have a protein that it has not been crystallized, and that protein is very difficult to work with, and we are actually applying MD for our prediction of the ligand binding. And of course, you can have different parameters, force fields in MD, and you can apply different ligands parameters as well. So my question is whether your tool it's on a par with MD, or it's better, or it has some limitations.
I don't know about this. So we haven't compared to MD. I would expect we can't predict unstructured regions, since there's usually no coevolutionary information there. So
Yes.
I would predict that it's no on those predictions.
Yes, but I hope we can discuss this more next week. Thank you. It's really interesting tool. Thanks a lot.
Thank you.
Patrick, I was curious on where you specify the binding site. Seems like a really key piece of information, especially on large targets. I'm curious if in your benchmarking, if you were able to either through like just rejection of predictions that are outside of the binding site, or filtering down to targets where they were all basically in the right binding site, if we were able to do a more head-to-head comparison and how useful that information was in relation to the predictive accuracy of, say, like DiffDoc or something like this, where you don't give it that context information.
Yeah, no, I mean, we haven't really looked at this, so I can't really answer. If you don't input any binding site, I would say that it just doesn't work, because we trained it specifically to kind
of... So yours has a binding site, but if you gave that additional information to, say, DiffDoc, either
but
rejection
I mean,
sampling, would you
how would you do that? Because I mean, DiffDoc has not been trained with that information, for example.
Well, if it's making predictions in lots of different places, you just throw out the samples that are in the wrong spot, right?
Oh, you mean like that?
Yeah.
But do they put things in the wrong spot? I think in general...
Absolutely. Especially for like large targets and things like this, there's lots of targets they can go into.
Yeah, no, I haven't looked at that. So, but that would be interesting, of course. But I think it would rather be interesting to compare with these other methods that have not been released yet, right? That also predict the structure. So I see the problem is rather, I mean, the structure prediction of the complex, because I mean, of course, these other methods can perhaps be useful, but you have to have exactly the same binding mode, right? Otherwise, how would you get the hollow structure to start with?
I mean, obviously, with the Rosetta fold all atom, it's not released yet, right? So how do you?
Yeah. So I can't really compare to
At least for the methods that are released. Yeah.
Yeah, I mean, for the methods that are released, I would say probably if you throw away things that are on the wrong place, I would expect the performance to be a little better. But I still think that like that problem is a non-problem in a way, since you need a hollow structure as input, right? If you input the APA structure, it doesn't work. This has been tested.
Absolutely, yeah. So it's, yeah, you're using an additional piece of information that may be not a fair comparison in the benchmarking. Okay, more questions.
I could ask some questions. Hi, Patrick. Nice to see you. Congrats on the paper. I had a few questions. So is the accuracy of the protein ligand prediction dependent on the quality of the MSA of the protein? And how do you see this working with like designing new proteins that maybe don't necessarily have a lot of MSA information?
Yeah, so I mean, if you would be designing new proteins, you wouldn't really use an MSA, right? So you would only be like single sequence. Let's say you inverted this network and do some kind of gradient-based search or something. But I think you still kind of know what is supposed to go together, because what you kind of learn here is also, you know, you learn coevolution and what things are kind of supposed to be constrained in evolution. Otherwise, none of this would work. And this is also why these other protein design tools work with single sequences.
And did you, were you able to like deconvolute, like if the predictions were better depending on the quality of MSAs? Is that something?
No, we don't see any relationship with that, right? So I don't really know what makes predictions better. I think a big thing here is overfitting to certain proteins. I mean, you can see that on, you learn easily like similar proteins. So it only works in 1/3 of the cases, right? Well, it's almost half if you look at all proteins. And I think this is a big problem for the other methods as well. That's why I would like to compare. You know, so I mean, all of these methods that we compare with, they use different information. I mean, a lot of them also encode the pocket or even like atoms that are supposed to be with the ligand. And I mean, the only thing that has been released, at least the paper, is Rosetta fold atom, and they don't have the pocket. So I mean, we're more biased. But I can't really say, since there's really nothing verifiable from them yet.
Yeah, I guess it's really hard. It can be difficult to compare the accuracy of the different methods when there's like different information being.
Yeah, I think so. I think that's like, you know, all of them use completely different information, but I would still divide it on things that use hollow structures and not. Because, I mean, if you have the hollow structure, I mean, how do you get that if you don't know the complex? Like you probably wouldn't, right? So, but to the other methods, I would still, there it's easier to compare. And you could, for example, compare to how similar templates are, and what happens if you take away the pocket from us and so on. But since nothing is really available, we can't do that right now.
Cool.
More questions? I was wondering if you could speak more directly to the E3 invariance of how you're adapting the FAPE loss. I think it is there, but if you could talk a little bit more about like in particular the translation and rotation that comes out of the alignment from the FAPE. Does that still carry over when you're using just the individual atoms from the ligand, or would it be worth in exploring encoding the symmetries, you know, the different symmetries of rotation and translation more directly into the loss function?
Yeah, I think it may be an idea to do that better. I mean, now for the atoms, as I mentioned, we don't have frames. So everything is only seen from the protein frames. But since the ligand is so much smaller than the protein, this doesn't matter in the same way. I mean, if the ligand was much bigger than the protein, then you would have a big problem.
The protein isn't moving very much when you move the atom. The center.
Yeah. So no, but you still see everything from the frames of the protein. So you still have basically fate. It's just there's no ligand fate, so to say. It's protein and protein ligand fate, but it's no ligand fate for itself and towards the protein. But
And I guess
think
because you're using the atom graph from RDKit, do you have to worry about like the symmetry of, say, flipping over a tyrosine? Like there's if you relabel the atoms differently, it's the identical ligand, but maybe you don't have that issue.
I'm not sure I understand the question.
If you have like a phenol ring, you can do like a 180 flip on it. And it has the atoms in the identical positions, but the armistice is high because it's not the same position.
Yeah, I mean, this is something I thought about in coding, but then I realized this is like, it almost never happens, that you have a ligand where you have this problem. It's like less than 1% of cases. And that's why I think it's not really a problem.
Okay, fair enough. More questions?
I have a question that's also a little bit more technical. I was curious when you talked about like the MSA representation, and you kind of just concatenated the ligands atoms onto the end of that. I was curious how you determined an ordering for the ligand atoms, because there's no real canonical ordering for a molecule or a molecule graph. So I was wondering how you kind of embedded that.
Yeah, so I mean, we just use whatever RDKit gives us. I don't think it really matters. It's, I mean, if you flip the order, it's like it's still kind of free, right? So all the network really knows is the bonds, and this kind of tells it the order, or like where to put things at least.
Right. So in the attention modules, there's some sort of positional encoding usually to kind of help bias the information that's being passed around. Do you exclude positional encodings for your ligand atoms, or do you still have like some sort of positional encoding there?
I mean, for the triangle attention and stuff like that, you still, we still have this positional encoding. It goes into the network, but I can't say how much it uses it for this case, because I think it's kind of confusing. What you can really say is, I mean, the ligand atoms are so few, so they're all kind of close in position, no matter what you do. I think the positional encoding is more for, domains in the protein and also between the protein and the ligand. But I think there's a lot of changes you can make here. And I mean, this is only our really first version here we released. So hope to try some more things.
Thank you.
So you mentioned more data and better loss as sort of opportunities for improving predictive accuracy. Obviously, we have a long ways to go to get to 90%. But I'm curious if you could talk a little bit about the other dimensions of scaling laws that people have identified, which is network size and training time. And I see you're getting some overfitting. Maybe that relates to getting like the right loss function. But I'm curious if you did any studies on like making the architecture smaller and seeing that there's kind of a trend in terms of getting worse quality. And if you made the model bigger, it would get better quality.
Yeah, no, I haven't looked at this, but I don't think making it bigger, I think is bad idea, because I think like when we also train this for proteins only, it's very easy to overfit. I noticed, and I think that actually, I mean, maybe I shouldn't say, but I would AlphaFold is overfit in some ways, right? Because you have a lot of, like, for example, DNA binding sites, or you have some kind of heme group or ligand that it shouldn't be in the information. But as we also see, you can learn the pocket perfectly, even though, I mean, it shouldn't be possible. So I think what's going on there is really overfitting. And if we would train this kind of as long as, DeepMind did, we would overfit to the protein, but we wouldn't learn the relationship with the ligand.
More questions? So you mentioned very briefly that you're trying to make this universal, and so going towards, say, nucleic acid or other things. Will it take new ideas, or do you think that it's just a matter of getting the right training set and just letting it rip?
Yeah, I mean, nucleic acids will never happen. I'm not really sure why, like, this is now trying to kind of be sold as I see it. Because if you look at the performance there, especially in CASP, it's terrible. And the classical methods that have been around for 20 years are still much better on new things. I think the evaluation here, as I mentioned, is important. If you evaluate on RNA sequences that are 60% similar to what you train on, I mean, chances are the structure is going to be identical, and then you're going to be able to predict this very well. And then you're going to have somewhere around, you know, what the LDDT shows there. But if you take something new, it's not going to work. And there are very good reasons for this. There's no co-evolution. And this is something I've been working on also myself. And I can get exactly the same performance, but I don't think it works. It's I have never seen anyone predict anything new regarding RNA that, you know, turned out to be accurate.
So there really is just a missing training data problem with a lot of these.
Yeah, information. I mean, you don't have anything to constrain it unless you have something similar, you know, co-evolution in RNA. You can't do it. And I mean, RNAs don't co-evolve. That's pretty well known.
More questions?
I have another question. I might have missed it, but I was curious how you encode where the pocket is that you're kind of trying to bind it. I might have missed.
So it's a one-hot encoding of the residues. So yeah, we just add basically that, and then like an extra feature. This residue should be in the pocket.
Okay, cool.
So like how sensitive is it to getting like the specific residues? Like if you get it wrong, will it still be able to get it in the right spot, or like, you know, how?
No, I don't think so. I mean, as I mentioned, we haven't really looked into this properly. So, but I think it shouldn't work because I mean, we explicitly tell it, you know, put these things together. The pocket is here. We just don't know how. So I would be very surprised if it worked without pocket.
And you're using all of the residues within 10 angstroms, is that right?
Yes. So all the C betas within 10 angstrom from any ligand atom.
So when I tried using the CoAb, it was not like super clear exactly how to do that. Is that something that you're going to make sort of in the next version where it's more user friendly?
Yeah, in the next version we will remove this since, you know, there's been a lot of issues. Like I think you could probably reach very similar performance just throwing this away. Like if you look at, I mean, drug discovery so far, the problem has really been kind of how to put the ligand in the pocket. And there are a lot of, I mean, if you go to pharma, they've been using the same pockets forever, right? So I think there are some new pockets, and especially if you don't know the pocket, I mean, it would be super useful if you can put it together. But I don't know if anyone has really tested this on, you know, like new pockets. I think most cases the pocket on the protein should be pretty clear, and in those cases probably where this works.
More questions? Okay, well, if there's no more, thank you so much, Patrick, and let's give him a hand. I really enjoyed your presentation. It was really clever details.
Thank you very much.
The method is very impressive, so thank you.
Thank you. Oh, take care. Bye.